Yeah.
And let's start by providing you a few useful links. So if you go to the atos.net/myqlm, you will arrive on a landing page of the ATOS website where you can have all the required information regarding myqlm. So to answer one of your question, you've got a links on the sites and all the GitHub environments regarding myqlm directly from there. So if I go in the documentation part, what you can see, you have also hosted on GitHub a full documentation of myqlm, and you will have a very interesting way to progress into this documentation with a first basic usage of how to write circuits and simulate them by executing them on one of the simulators. And you have advanced usage, and we provide also, so for example, if you want to install myqlm, that's very simple. You have some prerequisite for sure. It's Python based, so we only support at the moment Python on Linux and Windows, and we plan to support it soon on macOS as well. And to install a myqlm is as simple as just typing pip install myqlm. So you have a few additional steps after that if you want to benefit from advanced feature to visualize your circuits and so on. But by default, with just pip install myqlm, you will have all the basic modules. I can show you also in the documentation we have some links. One link to MindBinder, and in MindBinder we provide a full set of tutorials, and these tutorials can really help you get acquainted with the programming with myqlm, coming from very beginner notebooks. So okay, the first time I launched MindBinder, it's a little bit long because it has to create a whole virtual environment, but after that it's quite speed. So you can see the notebook. You can start with basic examples, and after that we will go through some of them. All the details about the language, the simulators, and remember the only simulator we have by default is a noiseless simulator. If you want to take advantage of advanced simulators or noise simulators, you need a QLM itself. So on myqlm you have only the open source simulator, and you have several examples on more advanced circuits like variational algorithm, and I will show you one of them. You can develop your own plugins, and I will explain how to do it, and everything that is required to import and export circuits that were made on other frameworks. So all the documentation is available on a MindBinder. If you want, you can also import all these notebooks to run them locally. So this is what I've done, and I've got a few of those tutorials, and what I'm proposing here is to run a few of them to give you a better understanding of how to program with myqlm. So do not hesitate to interrupt me if something is not very clear at one time or another, and I will try to detail. So let me put my screen in full screen mode. It will be easier for everybody to see. Okay, so let's start with the basic, the kind of hello world program for Quantum. We will create an entangled pair of qubits. So first thing to do, as it is Python, we have to for sure import our modules. Then first step, we instantiate a program. when we have this program, we want to manipulate some qubits, so we allocate qubits. In that case, we allocate 2 qubits. And after that, we start applying some gates to those qubits. So typically here we apply an Hadamard gate on the first qubit, and after that a CNOT gate on the pairs on both qubits. So I execute my circuit, and then I have my program, and from this program I create a circuit and I display this circuit. So really, this is a very simple example. You can see my 2 qubits gate and a control NOT gates apply to the second qubit. So if you are already familiar with quantum programming, you already know this pattern very well. For the other, maybe I can give you a few more information. So you have the 2 qubits by default. The convention is to start always with the qubit at state 0. So the 2 qubits are at state 0 at the beginning. When I apply my Hadamard gate, I will do rotation and I will put my qubit in a superposed state. So in this superposed state, I have the 2 states 0 and 1, which are at the same probability level. And when I apply a CNOT gate is just a control NOT gate. That means that this gate is a NOT gate. So what is after the gate is the opposite of what's before. It's just a simple inversion gate, but that is controlled depending on the value of my first qubit. So if I want to simulate my qubit, what I need to do is I have a circuit, you have seen it. From this circuit, I will create a job. So this is my circuit to job, and I will submit this job to an execution stack. So an execution stack is something that is represented here, maybe a little bit complicated for a first example, but you have your circuit that is pushed through different plugins up to a QPU, so a quantum processing unit. That can be a real QPU or it can be a simulated QPU. In our case, it's a simulated QPU, and we use the PyLinalg simulator, which is the linear algebra simulator. For that case, in my case, the execution stack is only made of PyLinalg. I don't use any plugin. So I create a job from my circuit and submit this circuit and submit this job to my execution stack, and I get the result. And if I want to visualize the results, what I see as a result, here I have a 2 qubit system. So my 2 qubit system can have 4 different states, 0, 0, 0, 1, 1, 0, and 1, 1. But in that specific circuit, after applying the Hadamard and CNOT gates, what I see is I got only 2 different states with the same amplitude. That means that the 2 states have the same probability. It's state 0, 0 or state 1, 1. So at this stage, we can see that the 2 qubits are entangled. So really, this was a first very simple example. I don't know if you have questions or if things are not very clear. Okay. So let's go back to, sorry, to another example, maybe a little bit more complicated. So let me put my screen in full screen. Okay. So in this second example, we are doing a quite famous experiment, which is the qubit teleportation. So the qubit teleportation, it's at least a way of presenting that. We have a qubit which is in a specific state, and what we want is to transfer this state to another qubit, which is kind of a qubit teleportation if we want. So first, before talking about teleporting qubits, I just want to remind you a few notions. I'm assuming that most of you are really familiar with all these notions, but just in case, it's always good to remind them. So my qubits are working in a two-state space, and a single qubit can be represented by a vector. It's a linear combination between the two states, state 0 and state 1, and the two linear parameters I have, alpha and beta, are just expressed either by a simple vector. So I can explain my qubit state by this vector. And we are talking about state superposition because a qubit can be in a linear combination of the two states at the same time. But remember, it's quantum mechanics. When I do the measurement of my qubits, I'm losing this superposition state, and my wave function is collapsing, and I just measure either state 0 or state 1 with a probability that is linked to my parameter alpha or beta. So when I do the measurement of my qubit that is in this specific state, I will get either 0 with a square of the norm of alpha, or 1 with a probability square of the norm of beta. And for sure, I have either state 0 or state 1, so the sum of the probabilities for sure is 1. Most of the time we do not use the vectors notation, but we use a more convenient notation, that is the direct notation, which is completely equivalent. We represent our two states, 0 and 1, with a bracket notation, and we define our qubit as a alpha alpha of state 0 plus beta of state 1. And there is an easy way to represent a qubit, a single qubit system on a sphere, which is the Bloch sphere, where we can simplify this notation. Remember, alpha and beta are complex numbers. So to represent them, there are 4 different numbers, so the real and imaginary parts of each alpha and beta, but they can be represented on a sphere, knowing that alpha square plus beta square is equal 1. So when the alpha and betas are changing, you can consider they are moving on the surface of the sphere, and by convention we say, for example, state 0 is corresponding to the North Pole, and state 1 is corresponding to the South Pole, and we have a representation with angles to explain where. So when we apply some gates on a single qubit, basically what it's doing is we are moving the position of the qubit on the surface of the sphere on a different part. So when we apply rotation around the x-axis or y-axis or z-axis, it's just applying the same rotation as if it was on the sphere. And just because I will use this term, by default the standard basis is 0 and 1, but there exist other bases. like the minus plus basis, which is called the bell basis, that can represent also the state of a qubit, but in a different basis. So having said that, let's go back to our circuit. So you are already familiar with writing a circuit. So we import our modules, create a program, allocate our qubits. In our case, I have 3 qubits. One will be the source qubit. The first one will be the first source qubit. The third one will be the target qubit. And we will use an ancillary qubit to do the teleportation. So first, what we do, we create an EPR pair between the ancillary qubit and the target qubit, and you already know how to do it. And then we will rotate the first 2 qubits into the Bell basis. So after that, we do a measurement. And remember, the measurement, it will be a way to measure. So to do the measurement, we have to allocate, in that case, not quantum bits, but classical bits. So we do a C-alloc, which is an allocation of 2 classical bits, and we do the measurement. So we measure source and ancillary, and we put it into the array results. And after that, the array results is made of two parameters that are the measurement of 2 qubits, and we apply the results of the measurements of these 2 qubits by applying a rotation around the X and around the Z axis to the target. And let's see how the circuit looks like. So we have in our very simple circuit here 3 qubits. So first we have made the EPR pair between the ancillary qubit, which is the middle one, with the target qubit. We do the measurement of the Q0 and Q1 in the Bell basis. And C0, we apply an X rotation, and C1, which is the result of the second qubit, we apply a Z rotation on the second qubit. And hopefully, the state of the qubit 0 will be teleported, as we can say, to the third qubit. So what I said, by default, all the circuits are initialized in the 0 state. So it means that all our 3 qubits are in the 0 state. So first, what I would like to do first is to create a random quantum state. So to do my random quantum state, what I will do is I will prepare an array of 2 angles and apply a rotation around the x-axis and around the z-axis for my first qubit. So let's display first what I mean by applying a random rotation. So here I've created a kind of initialization circuit working only on the qubit 0, where I applied a random angle on the x-axis and a random angle on the z-axis. So let's see on the block sphere how it looks like. So in my program here, I have plotted on my block sphere some different state. So initial state, after the first rotation and after the second rotation, and I've drawn a trace. So what's happening here is you have your initial state. I said the qubit is at the 0 state. We apply first rotation around the x-axis of it's nearly a pi, so it's nearly a half turn around the x-axis. And after that, I apply a second rotation. It's nearly pi again. It's random, so okay, around the z-axis, and I can see. So my qubit 0 was in the 0 state initially, then rotated, and you can see on the block sphere the kind of operation you can have with a simple rotation gate. So now what I want to do is combine my initialization circuit with my teleportation circuit. And I can do it by simply using a plus operator. So when I use a plus operator, I have my initialization circuit here and combined with my teleportation circuit there. Now, the only thing I want to do is simulate both the simulation of just the initialization circuit and the simulation of the full circuit. And remember, to do a simulation, I have my circuit, I converted my circuit to a job, and I submitted this job to an execution stack, in my case, PyLinalc. So when you have a circuit, you can get the results just in a single line. So what we see here is I look at my initial state of the system. Remember, the system is made of 3 qubits, so I have potentially 8 different states. So what you can see here, initially, everything was at the 0 state. After my initialization circuit, what I see is I have my 3 qubits system, where I see the only difference is on qubit 1, and I have the amplitude of the qubit 1. And after teleportation, what I see is the only difference is on the qubit or the 3rd qubit, or it was qubit 0 and qubit 2. And what I see is my qubit 2 is having the same state vector as the qubit 0 before teleportation. So we have done in that case, we could consider we have done the teleportation. If you have any question, do not hesitate to interrupt and jump into the conversation. If there are no other questions, I propose we go to the next circuit, and we increase progressively the complexity of the circuit. And we are talking now of a famous algorithm that maybe most of you already know very well, the Grover algorithm, and to see how to implement the Grover algorithm on my QLM. So Grover's algorithm is an interesting circuit. The goal is to find a solution that is hidden into a black box. So we'll consider a black box which is made of a function, and we want to find which parameter of the black box. And to do that, we will query the black box several times. And the goal and the interest of the Grover's algorithm is you have to query what we call the oracle only a number of times that is in order of square n being the number of possible solutions. So let's see what we mean by an oracle. So let's consider first a very simple function, that is providing 0 as a result anytime except when the input parameters is equal to a specific value, the omega value. And the goal is how many times should I query my oracle to find the omega value. So if you are working, I would say in classical with classical bits, you have omega that is a value between 1 and n. So you have n different possible solution, and how many times you should query the f function to find the value of omega. By default, you have no clue about where is omega. You have completely unsorted search to achieve. So by default, you will try every solution, every possible solution. So you will try f for the values 1, 2, 3, 4, 5, up to finding omega. So by in average solution, you will try n over 2 times before finding the right solution. So the order of magnitude of finding a solution like this black box is the order of magnitude is n. Now let's translate this problem into a quantum problem. We've got an operator u, which is on the same construction, where u applied to a specific state will return by default always this specific state. So this operator is the identity if the state is different from omega, and the operator is the not function if the entry state is equal to omega. And here again, the question is, how many times should I query my operator before finding the right value of omega? So let's start with a simple initialization. So in my simple initialization, we can play with the number of qubits. So let's say we are using six qubits in that case. So that means that we have for omega 2 power of 6 different possible values. So that means 64 values, and I can choose any of these 64 values between 0 and 63. So let's say, for example, okay, I will define omega, or maybe whatever value. Okay, let's say omega is state 011,001, which corresponds to the in decimal format the value 25, and I will create an oracle that will be the identity if you apply the state, every state, except if you apply state 25, it will be acting as a NOT gate. So to create such an oracle, we are using one interesting function of the QLM, which is the abstract gate function. The abstract gate function is a function to create a kind of synthetic gates, either by providing the matrix definition of the gate, or by providing a circuit that describes the gate. This is what we are doing in that case. So you have to believe me that I am creating an abstract gate, which is called BB, like a black box, which will take 2 parameters. The first parameter is the number of qubits of my gate, and the second parameter is my omega value. Remember, my omega value was 25. Now I can visualize my oracle. So I create a program. I have a black box a black box gate created from my abstract gate, and I will I will allocate the number of qubits. I will apply my gates, and I will create a circuit from that, and I can visualize my circuit either at depth 0. So at depth 0, what you see is I've got a circuit with 6 different qubits, but I don't know what's inside. And if I go into the depth 1, I can see what my circuit looks like. Okay, so in fact, all we have to manipulate now is a gate. As it is a black box, we don't know what's inside, and the goal is to find which value of omega is the right value. And the goal is to find it by using as low as possible the number of query. So to do that, we create an amplification routine. This is the heart of the Grover's algorithm. And here again, I will use an abstract gate to do it. Just create a plotting routine. I could have put it in an external file. And now I tried creating my circuit. So first, the algorithm, the Grover algorithm, what the algorithm is doing first is creating Hadamard wall. What are we saying when we say an Hadamard wall? So we create a program. So now you are familiar with writing a circuit with my QLM. You allocate the number of qubits, and for each qubits, we apply an Hadamard gate. We create a circuit from that program, and we can display the circuit. Why the circuit is not displayed? Sorry. Oh, yes. So this is my circuit. Oh, I know why. Let me change my visualization tool. It will be. So I visualize my circuit, and after that I create a job, and I submit this job to my QPU, my execution stack, which is made of a single QPU, and I plot the results. So what's happening here? By default, remember, before applying the Hadamard wall, all the qubits were in the same state, 0. So my whole 6-qubit system is a single state, 0, 0, 0, 0, 0, 0. But now when I apply my Hadamard gates, I will have all my qubits in a superposed state. So that means that every possible state, so state 0 to state 63, are in the same probable state. So what I'm plotting here is the probability of having one of the 64 states, and you can see all the qubits are exactly with the same probability. Now, what Grover has demonstrated is we will use an iteration. We will use several times the oracle. And what Grover has demonstrated that there is an optimal number of iterations that should be made to get the most probable result. So there is a simple formula to find k matching entries among n. In our case, I have encoded in my black box only one entry, which is, you remember, 25 among n, which is 64. So if I do the calculation, in my case, what Grover is predicting is I need to iterate 6 times my algorithm, my gates to get the result. So what should I iterate? So by default, I have my Hadamard wall, and I'm applying my black box gate and my Grover amplitude gate. And if I look at the result, maybe can I look at the result? What I see here is after running a single iteration of my black box and Grover gate, I already have one state that has a higher amplitude than the others. And you can see already it's my 25 state. So it's pretty good. But if you look at the probability of having this result, the probability is close to 13%. So that means that I have one chance out of 8 if I do a single measurement to get that result. So 1 out of 8 it's not very good. So what I do is I will apply again the black box and the Grover and increase the size of the circuit. So at each iteration, I will do exactly the same. And what you see, after a second iteration, my chances to find the right state, the 25 state, has increased, and now it's close to 33%. So I have got now one chance out of 3 to measure it. And I go on. So a third iteration, and my amplitude has continued to increase. And a fifth, yes, 5 iteration, and I'm now close to 51%, 81%. And now I'm doing oh, sorry, I have to count 1, 2, 3, 4, 5. Okay, no, this is the 5, and I'm close to 95%. And if I do a sixth iteration, what I see is I've got the result with a probability close to 100%. So that means that if I run this circuit, I have query my black box 6 times, and after querying my black box 6 times, if I do a measurement of my circuit, I will get the result with a probability close to 100%. So this is exactly all what is the Grover algorithm about, is being able to use a black box the least possible, and to find the result with the most probable, the highest probability. So maybe if you are curious, I have done it 6 times. If I do it a 7th time, you will see my probability start to lower again. So really, the value of 6 is an optimum. So in conclusion, if we use a classical algorithm to do search on black boxes, you will have on average to query your black box function n over 2. So the order of complexity is n. But if you use the Grover algorithm, the complexity is a square of n. So we get with Grover a quadratic speedup, and Grover, it has been demonstrated that the Grover algorithm is optimal. So no other algorithm can be better in terms of order of magnitude. But to prove that, it's a little beyond the scope of the tutorial. So how things are doing so far?
I have a quick question.
Yeah.
So this is just something that's always confused me about Grover's algorithm. So it seems like in order to be able to design your black box gate, you need to already know the answer.
In fact, you can create your black box without knowing how to create your black box. But sure, you have to know the answer, and this is. But the goal is not to find the answer by creating something that has the answer. The goal is to see how many times should I query my black box to find the answer. And this is where really the Grover algorithm is strong. Is it will reduce significantly in that example. If I was using some kind of classical computing, if I have to find the value 25 among 64 different possibilities, I will have to query f with the value 0, value 1, value 2, value 3, value 4, and so on, up to 25. So to get the result, I should have queried, in average, 32 different states. Here, in average, I have queried 6 different. I have queried 6 times the operator. But what is, remember, in my case, I have created. Sorry, I have created a black box from a circuit. remember my black box from a circuit. If I show it, I've created from my circuit. But sometimes the really difficult part is to create the oracle, the black box. The black box is not always easy to write with a simple circuit. So you can define it by applying, for example, by defining a matrix, and sometimes it's easier.
Okay. Thank you.
Maybe I can add an additional comment in general on the consensus. The way to think about when you use this black box is to envision that you have a function that can, when you give an input, it can tell you if yes or no it's the right answer. So what you can do is like think of it as a function when you will evaluate the function at each point. And the advantage of using a quantum black box is like you can evaluate basically a superposition of inputs. And so this gives the right advantage, because otherwise, yes, it wouldn't make sense to use already the solution to build the black box. So usually it's what it's done to show an example, but usually when you deal with satisfiability problems or that kind of stuff, you can define functions that will eventually just try to evaluate the function they're trying to optimize in some sense.
Yes, and even with a simple function, I could have created a circuit that will have behaved on several different inputs, and this is where the function the Grover's function here. Sorry, maybe I can. Oops. The Grover function here is valid if you have in your black box several entries. So if you have several entries in your black box, you will be obliged to query a higher number of times, but this is still valid.
Okay, thank you.
If there are no other questions, I wanted to show you something maybe a little bit more, I would say, practical in terms of a variational algorithms. So Sabine explained you that variational algorithms can be used in many different applications. So you got a variational algorithm for chemistry, you get variational algorithm to solve linear equation systems, and you have a variational algorithm, one of the most famous one, the QAWA, that is used to solve classic combinatorial optimization problem. And I'm interested here in one simple problem, which is the max cut problem, and we will see how to solve it with a variational algorithm like QAOA. Okay. So we have presented you quite rapidly before what is a combinatorial optimization problem, and most of the combinatorial optimization problem, many of them at least, can be reduced to classical mathematical problem, and I've just mentioned a few of them. So they could be graph problems, and max-cut is one of the most famous. So in max-cut, I have a graph here, and I want to split my graph into two subgraphs in a way that I will maximize the number of edges that are linking the two subgraphs. So in my example, I have a graph with 5 vertices, and the optimal solution is to divide my graph into two subgraphs, the subgraph with the white vertices and the subgraph with the black vertices. And if I look at the way we can cut in two, you will cut through 4 edges out of the 5 of my initial graph. So this is a very simple example that you can solve by hand. But when the number of vertices in a graph is increasing, the number of possibilities is exponential, is exploding. So you will be in a situation where when the number of vertices in your graph becomes too large, you cannot just consider all the possible solutions. You cannot do any brute force resolution, but because it will be too time consuming. So everything is all about with the quantum computing. Quantum computing is providing a way to optimize the finding of approximate solutions. So MaxCut is an example. Graph partitioning or graph coloring is another example. For example, graph coloring, you have all your vertices that are connected with edges, and you have to find the smaller number of colors, such as two vertices that are connected must be of different colors. You have also a K-clique, which is a problem of finding Hamiltonian graphs, subgraphs into a graph, or a number partitioning. So all these kind of problem seems to be very mathematical problems, but can have a very practical application. Just to give you an example of a problem we have solved recently with one of our customers, with EDF. EDF in France, which is the energy provider, wanted to solve the problem of finding the solution of where to position a charging station for electrical vehicles, and finding a way to optimize the number of charging stations. And this kind of optimization problem can be simplified, or can be transformed into a graph problem. And this is why this graph problem have many applications. So let's see how we can tackle this kind of problem. So what we will start by creating a graph, a very simple graph. See if the graph. Okay, I've got a graph. Maybe I can create a graph a little bit more complex. I can adjust. Oh, sorry, I can adjust the parameters to. Okay. This graph seems pretty good. So I've got a graph. Oh. Oops. Sorry. Do it again. Yes. Okay, so here I've got a graph with 12 vertices, and I've just represented my graph here. So I'm just using standard Python libraries, no my QLM involved here. So from that graph, how can I encode my problem? So we can define a cost function under the form of an Hamiltonian. That is a very simple one. So what we define are spin variables. Spin variables are variables that can have either -1 or +1 value. And we look at we define those those S variables. So S will be equal to 1 if the vertex U is in the first subgraph, or -1 if it's in the other subgraph. And what you see here, when we do the sum of for all possible edges in my graph, I do the product of my two spin variables. If they are in the same subgraph, either 1, 1 or -1, -1, the product will be 1. And if my if my edges UV are corresponding to vertices in the two different subgraphs, my product will be -1. So remember, I want to maximize the number of edges connecting my two subgraphs. So I just need to minimize the energy corresponding to this Hamiltonian, and I will encode this Hamiltonian into a circuit. So how to do it? It's very simple because we already provide all the libraries to do so. So the only thing I have to do is I will use a very simple maxcut encoding function, taking into parameter a graph, and just print my problem. So my problem, as you can see, is made of 12 variables, my 12 vertices, and 25 clauses, which are my 25 edges. Yeah, I'm sorry because it seems that I do not have sorry, I think some parameters in my configuration that is not working correctly because I cannot access to my scroll bar. So I'm sorry, I have to put my screen a little smaller. I hope you can read it. So what I will do first, yes, just to explain you how QAOA is working. So what I will do is create a quantum circuit to encode my Hamiltonian, and what I want to do is calculate the energy value and to minimize this energy value. And this circuit will get into in parameters some angles, and what I will do is I will try to optimize by a classical optimizer the value of the angle to get the minimum energy level. And I will iterate. So the optimizer can be a classical algorithm like gradient descent, or in that case, I will use a COBILA, a constraint optimization bar linear approximation, that is provided directly from the SciPy library. So what I will do is I will iterate between a quantum circuit that will be simulated by my QLM, the result of the energy of the circuit, and I will modify the angle up to having either finding, I would say, a minimum when I reach a threshold, or if I don't reach this threshold, I will stop the iteration after a number of iterations. So let's see how to create first the circuit. So remember, I have created my problem, and now I want to create my circuit. So what I do is just I'm using a function coming with our combinatorial problem class in Python that will create an ansatz, which is basically the job I will submit to my simulator. I can create a circuit from this job and see how many gates are in this circuit. So I have got here, probably if you are not in a hurry, I can try to visualize those gates. Yeah, I can see the gates. No, I cannot see them. Sorry. This is my circuit, and I've got a circuit with many, so 273 gates with rotation, and this is a parametric circuit, so it will take into parameters a few angles. Now, what I want to do is simulate this circuit. So remember, to simulate a circuit, I create a job from this circuit and submit this job to my execution stack. So in my case, I will create an execution stack that is a little bit more complicated than what you have seen so far. So my execution state, okay, I import my modules, and my execution stack is here. I will, to simulate my circuit, I will go through an optimization phase. So my optimization is my SciPy plugin using the method cobila. I have limited the number of iterations to 200, and the tolerance, which is the level when I consider I've reached the minimum level of energy, to 10 power of -3. And what after this optimization plugin, I will use a display plugin, and I will show you the display plugin, how it works. It will display in real time the energy value at each iteration, and I use the PyLinal, which is my QLM simulator. So let's execute this circuit. So what you can see here is we have in real time for each iteration. So remember, I have a circuit with 273 gates, which is a parametric circuit. So at each iteration, I will submit different values of the parameters as an input, up to find the lowest energy level. So here, my iteration has stopped. If I look at the result, it told me that the optimization terminated successfully. It has made 113 evaluation of my function, so 113 iteration. And what I've got here is the 6 parameters of my QAOA circuit. So that means that if I use these 6 parameters as an input to my parametric circuit, I will get the lowest possible results, which is evaluated here. So now what I can see is I will do some checking. So I take the parameters here and apply. So I take the parameters from my results. What you have seen is my previous job was a parametric job. So now I fix these parameters, these optimal parameters in my circuit to create a circuit that is no more parametric, but which has a fixed value for the angles. And I'm submitting this circuit to my PyLinal jog to get the energy. And as a result, I can see, I can check the energy level, which is exactly the same that was here, so no surprise. And what I see after that, I look at the different probabilities I got. So my circuit was made of 12 qubits. So what I do is after simulation of the circuit with the optimum angles, I find the most probable state from my circuit, and the max probability has issued this specific state, which is 10110010 state, and that corresponds to my 12 binary values that you have seen before. So if my that means that if my vertex 0, I will put it in the second subgraph, my vertex 1, and all the vertices with the value 0 will be in one subgraph, and all the vertices with value 1 will be in the second subgraph. Just to illustrate them, I can draw them. It will be easier to understand. So remember, we've got the circuit first that was here. I don't remember. Okay. Oh, no. Oh, sorry. I created another graph. And here I have got the results where you can see in one color the subgraph, one subgraph, and in another color the other subgraph. And this is known to be a good approximation. And if I look at the max cut, it told me that in this graph I had 25 different edges, and this partitioning told me that my max cut is evaluated to 21. So probably for small graphs like this, I expect it to be the best solution. But if the number of vertices increases in a graph, the problem to find the best solution is intractable. But you get here a good approximation. So typically what I wanted to show you are some more advanced functions that are available in my QLM. If you have a problem that can be encoded as a either max cut or graph partitioning or graph coloring or existing routines that have automated the resolution in my QLM, it's easy because you have seen it's a matter of a few lines. If your combinatorial optimization problem is not part of the existing problem, what you have to do is to write your problem either in a Ising form or in a Cubo form. So what you have seen before is the Hamiltonian, in that case, in a Ising form with spin variables. In the Cubo form, it's a little bit different, but it's binary variables, not very different. So you have to write your Hamiltonian, and we have all the function to import this Hamiltonian and encode it in a Cubo form or Ising form, and after that create all the circuits and all the routines to solve the problem.